how to graph rational functions, and then we will talk about rational inequalities, how to solve them. So just a quick refresher, when you are working with rational functions, whatever polynomial you have in the denominator cannot equal 0, because anything that is in the fraction format, obviously division by 0 would be undefined. So even with rational functions, we have to make sure none of our denominator functions are going to be 0, which actually leads you into calculating your domain, because anything that would make your denominator a 0, we exclude those numbers from our domain. So we have looked at that. As it also happens, the numbers where your denominator becomes 0 is the same place where you are going to have vertical asymptote. So remember, that is where you have these imaginary lines. Basically, that would be a vertical asymptote there. So they are imaginary lines where your function gets really close to those lines, right? But it's never going to cross them, definitely not touch them. Now, vertical asymptotes, your graphs do not cross them at all. Horizontal, and we saw an example last time. With horizontal asymptotes, you can actually still have a part of your graph cross it. So it can, because remember, we had that one function with the x-intercept, so you were actually crossing the x-axis. So same thing can actually happen with oblique asymptotes also. So with oblique asymptotes also, your graph can technically cross the oblique asymptote, but for vertical, it's a hard no. And the main reason for that is because the domain is undefined at that number, right? So you can't really have your function cross at that point. So to calculate your vertical asymptote, you basically do the same thing as your domain, is see where the denominator will be equal to 0, and that's where our vertical asymptotes are going to be. Horizontal, it actually depends on the type of function you're going to have. So if you have a function in the form of something like this, where you have a constant number on the top, and then your x is on the denominator. Now it can be x by itself, it can be a polynomial on the bottom, it doesn't matter. Whenever you have a function in this form, which we would officially define it as if the degree of your numerator is less than the degree of your denominator. I'll say that one more time. If the degree of your numerator is less than the degree of your denominator, your horizontal asymptote is going to be at the x-axis, or in equation form at y equals 0. Okay. If the degree of your numerator is equal to the degree of your denominator, then the x-axis is not the horizontal asymptote. In that case, it's actually going to be the coefficient, basically the ratio of your leading coefficients in that case. So you have to look at what type of function you have. So if the degree in the numerator is less than the degree in the denominator, then your x-axis, or the equation y equals 0, is your horizontal asymptote. If the degree is equal, so the numerator and denominator have the same degree, then in that case, your horizontal asymptote is going to be the ratio of your leading coefficient. So that was an example we had seen. Something like this guy here. So you can see we have x to the first power on the numerator, x to the first power on the denominator. So the leading coefficient for this guy is a 1 on the numerator. The leading coefficient is 2. So you can see that's the ratio of your leading coefficients. So whatever in the, the largest value of your x, whatever those coefficients are, that's the ratio you're looking at. Now, if the degree of your numerator is larger than the degree of the denominator, that's where the oblique asymptote comes into play. So you will not have a horizontal asymptote in that case. You will only have an oblique. So this is where the numerator has a greater degree than the denominator. And in that case, you are using synthetic division or long division to find your oblique asymptote. So those were the 3 different types of asymptotes we had talked about, and that's kind of where we had left off. So when we're talking about drawing graphs for rational functions, of course, you would start out with those asymptotes. You start out with the domain of your function. And like I was telling you guys last time, we're not really drawing graphs by hand because you're choosing, but a lot of these techniques will still come into play. So of course, we're not going to be drawing them as dashed lines or stuff like that. But we will still start by finding out where our asymptotes are, which ones do we have. Now, all functions will have a vertical, but then, like I said, you either have horizontal or oblique. Symmetry always helps, so we can check for symmetry. If your graph is crossing the X or Y axis, it's nice to find out what those intercepts are going to be. Now, again, if you were graphing by hand, then you do want to select other points, so you get the general idea of what the shape would look like. And then, of course, the last part is drawing your graph itself. So for an example like this one, we'll identify some of the main things and then see what the graph should end up looking like. So, did we actually look at this one? I can't remember. This is actually the same function that we looked at in multiple different examples. So you can see this is the example 2 over here, and this was also the same one from example 1 over here. So we already have the horizontal and the vertical asymptotes from these examples. And you guys can see that in the notes for those of you who were not here last class. So our vertical asymptote for this was that x equals positive and -3, because that's coming from that denominator, right? X squared minus 9, set that equal to 0. This one will have a horizontal asymptote because the degree of my numerator is smaller than the degree of my denominator. So your y-axis is actually going to be your horizontal asymptote in this case. So if we had to draw them as dotted lines or dashed lines, that would be -3 here, +3 here. Now that I'm thinking about it, I think we did actually talk about this example. So that's how far the domain and the asymptotes is going to take you, is we know our graph cannot cross these lines. The horizontal asymptote you will actually, because when we found the x-intercept for this guy, oh, what did that x-intercept come out to be? Wasn't at the origin, was it? Let me see if I can find that. So remember, basically, when you're trying to find the x-intercept, you're making your y value 0, right? So you set your equation equal to 0, and you find your intercept. Where do we go? Yeah, so if you're taking your y value, setting it equal to 0, you will basically end up with x minus 1 over x squared minus 9. You will multiply both sides by x squared minus 9, which actually disappeared. And again, since I went over this last time, I'm not going to go over it again. You do end up with an x-intercept at x equals 1, which would be right over here. For your y-intercept, if you guys remember, we had come up with 1/9. Because when you make your x values 0, you end up with positive 1/9, which is going to be 0.11111, and that was, just shy of the origin where it would be. So like I said, these would be some of the starting places that you would begin when you're talking about the graph. Now, to imagine what the curve would look like, that is where we pick several points from each of the 3 intervals that you have. So you would pick several points from the left-hand side, something in the middle, and then a few points on the right-hand side so that you can get the idea of that curve. And then, of course, that guy would end up looking something like this. If we transpose that graph, basically what we're looking at is this curve coming down this way. So that's going to be, basically it's obstructed by the horizontal asymptote over here. So it's not going to cross your x-axis. And then it's of course getting obstructed by that vertical asymptote at x equals -3 on this side. So it's basically confined by those asymptotes. So again, if we had to draw them as imaginary dotted lines, this is where our horizontal asymptote is. Where is -3? This would be our vertical here, and then another one of +3. So you can see how that middle part of the graph definitely intersects, the y-axis intersects the x-axis, but then it's still bounded by the two vertical asymptotes. So that's kind of the behavior that's happening here. So intercept the x, sorry, the y and the x-axis, and then go down here. And then what was our last part? The right-hand side. So that would be going this way. So basically what I would recommend you guys to do is start by looking for the asymptotes where they should be. And then for some of the examples, they will ask you to find the x and y intersect. So anyway, you will have to, because you know how they do those multiple parts, so you would have to find them anyhow. So I think that's our next example, I believe. Okay, there we go. So sketch the graph of the rational function. Note that the function is not in lowest terms. Find the domain first. And they're clearly telling you your function is not in lowest terms. So that's actually going to have an effect when we start graphing it. But the first thing we want to start out by is finding the domain. So can you tell me what the domain of this function is going to be? Oh, I am so sorry, Jocelyn. I didn't realize I didn't do that. There we go. So can you tell me what the domain for this function is going to be?
Four to infinity.
-4 to negative. Negative to negative.
Oh, you guys are giving me only partial answers.
Negative infinity, -4, and then -4 infinity.
Yeah, so you gotta use both sides, right? Only thing you cannot use is the -4. Everything else we get to use. So just take the denominator, set it equal to 0. Which of course ends up giving you x equals -4. So yeah, not using -4, but everything else is okay. Okay, so we're gonna type that in first, negative infinity to -4 union -4 to infinity. So obviously then that tells us our vertical asymptote is also going to be at that same number. So automatically, it's actually going to eliminate some of the functions here for us. Let's make this guy larger. Where is that vertical asymptote being shown? Positive 4. It's being shown at positive 4. So you can already see C is going to be out of our option here. This guy. Does that seem like he could be in the play? No? So here's the thing, we know from the original function that we cannot use -4 because it makes it undefined. So even at -4, which would be this number over here, we cannot include that point, which is at -4, because my original function is not defined at -4. So that's actually why C and D cannot be in the running. So they're telling us specifically that this function is not in lowest form. So let's take a look at him. You've got x squared minus 16 over x plus 4. What can we factor that numerator into x squared minus 16? Because it can be factored. X plus 4 and x minus 4. Yeah, because you can rewrite x squared minus 16 as x squared minus 4 squared. Remember, you can use that difference of squares factoring. So that's exactly what you're doing with the x squared minus 16. That factors into x plus 4, x minus 4. And then as you can imagine, since we have x plus 4 and x plus 4 common, we can cancel that out and put it in the lowest form, which in its simplified form is going to be x minus 4. However, our original function is still this guy, what we started out with, and that tells us I cannot use -4 in my domain, so we still have to take that into consideration. So if you look at this graph over here,
That one's not.
oh, I don't want to put it to you, but I need to get rid of him. So you can see this is my -4, and it's still defined at that, right? The open circle is actually placed right here at +4. So again, this is not my graph. What did we have? -4. So the only one that we are then left with is going to be graph B. And you can see that was my mark for -4, and you can see I have an open circle right where -4 should be on that graph, because x minus 4 does come out to be a linear function, right? It's just a slope of 1 with the y-intercept at -4, just like your y equals mx plus b format. So that's the graph that's going to satisfy our original function, because you have that little open circle, which is telling me we are not including -4 in our domain. So B is going to be our graph, and we are good to go. I really want to do next question, but it's not giving me my notes. Okay. Questions on this one, guys? So you can see we didn't really even have to go and graph the function on a graphing calculator, because you had enough information that you could use process of elimination to find out what your graph is. Okay, let's take a look at another example here. Okay. This one actually is gonna be a pretty straightforward function. I wanted to do one with an oblique asymptote. Just to show you what this graph would look like, we have X on the numerator. Okay, so with this function. Okay, so can you tell me where our vertical asymptote for number 5 is?
Two, why? Oh,
Plus or minus 2,
what did you be two?
or just 2?
This minus the square root.
All right, let's see. So this is our denominator, set it equal to 0. To get rid of the square, we would use square root. Square root, of course, gives you plus or minus. So square and square root cancel out, leaving us with x minus 2, but 0 is actually one of those numbers, right? That does not actually take plus or minus. So it doesn't show up in the vertical asymptote. You only end up with x equals 2. And you can kind of see that, and I don't know why my little bottom disappeared here, but you can see that right over here. That's where your vertical asymptote is going to be, right, at x equals positive 2. Now, also, your numerator has a lesser degree than your denominator, because this is, of course, when you FOIL that, it's going to become an x squared polynomial on the bottom, and that's an x on the top. So since the degree of the numerator is less than the degree of your denominator, x-axis is going to become your horizontal asymptote. If you look at this graph, the arm on the right-hand side, is going to stay above the x-axis because it comes across, we can kind of zoom out a bit and you can kind of see if I can get this side aligned. So that one will get closer and closer to the x-axis from the top, but it's not going to cross it, obviously not going to touch it. However, we do have an x-intercept in this function, and you can kind of see that point right over here. So what's happening is the left arm of your graph is definitely crossing the x-axis, but then it still is running along the x-axis itself, just coming from the bottom. So of course you need to kind of zoom in for that a bit, but you will see this guy is on the bottom and it's still kind of running next to the x-axis, but at this point, because it's done the little crossing at the x-intercept, it will still stay very, very close to the x-axis and it's not going to cross it again. It's just going to run alongside it. So you can zoom out as much as you like, and it's going to keep that pattern, for the length of its domain. So it does not cross on the right-hand side, but it does cross that x-intercept on the left. But you can see how different this shape of the graph is just depending on, just kind of trying to align my asymptotes there, but just looking at the way, depending on what your polynomials on the numerator denominator are, each graph is going to be pretty different from, each other. You're not really going to see a whole lot of similarities outside of the, no asymptotes, domains, and those kind of things, but a lot of them are going to be unique in their own way. So these were both examples with vertical and horizontal asymptote. Let's look at an example of a graph with a oblique asymptote, what that would look like. This little paragraph over here is pretty important because it's telling you that your rational function cannot cross a vertical asymptote. So there's no way you're going to see it cross the vertical like it does with the horizontal. But with horizontal and oblique, it can still cross like we saw in the example just now. So vertical and no, but for the others, it can definitely have a crossing happening. So again, remember, when the numerator has a higher degree than the denominator, that's when you're seeing oblique asymptotes. Of course, we'll start out by finding the vertical one since they're easy to work with. What's the vertical asymptote on this guy? Yeah, very good. So take the denominator, set it equal to 0. X equals 1, which would be here. So like I said, you are going to have an oblique asymptote in this case. And for that, we can use long division or synthetic division. So again, you will see, I believe this is actually the same function we did before. You will need to put a space for the missing x term, so 0x in there. So when you set this up, we have 3 from the x squared term, 0 from the missing term, -4 from the constant term. You are dividing by the denominator, so since that's set up as x minus 1, technically you're dividing by 1. And since you guys already did this calculation last time, I'm just going to go through it quickly. So you bring down the 3. 3 times 1 is 3, add them. 3 times 1, of course, again is 3, and that gives us -1. That's the remainder. This is part of the quotient, and also the oblique asymptote, which comes out to be 3x plus 3. So when we try and graph this, let's see, you're starting out at +3. And I'm just using y equals mx plus b to help me graph this. So your y-intercept is +3, and then the slope of 3/1. So go up 3, right 1, or you can go down 3, left 1. So 1, 2, 3, 1. So this is kind of what our oblique asymptote would end up looking like. So of course, if you have an oblique asymptote, you don't have a horizontal asymptote. Now let's talk about what its x-intercept might look like. So for x-intercept, you make your y value 0. We will need to get rid of x minus 1. So since it's in the denominator, we basically end up multiplying both sides by x minus 1. And in this case, the x minus 1 cancels out. 0 times anything is going to be 0. So honestly, instead of going through all of that, just take the numerator, set it equal to 0, and you will get your x-intercepts. Because every time you set your y equal to 0, your denominator is going to disappear. So just save yourself some trouble. Just take the numerator, set it equal to 0, and that will give you your x-intercept. So anybody have idea what this guy will come out to be for our x-intercept?
Square root
Yeah, very good. And then we will need a decimal approximation in that case because it's not going to be a clean answer. Because you have an x squared, you will need to use square root, and square root will give you positive and negative. So what does that come out to be? Just as an approximate value, square root of 4 divided by 3 will be 1.15, positive and negative. Oh, 1.1. So remember, we have the vertical asymptote at 1, so it's just going to be a hair to the right of that guy. So x-intercept for y-intercept, we set our x equal to 0. So that would be 3 times 0 squared minus 4, 0 minus 1. What do you think that guy will come out to be?
-4, so just +4.
Yeah, very good, because 0 times anything is going to be 0. So this becomes a 0. This is obviously already a 0. You're left with -4 over -1. So just one number above where your oblique asymptote was. Now, again, if we were graphing this by hand, then we would be selecting a few more points to try and understand the shape of this graph, but I think we've got most of the important features here, and you can probably already guess at its shape because it's going to be blocked by those two asymptotes. But just to show you over here, what did we have? 3x squared minus 4. And then the whole thing divided by x minus 1. And actually, just to show you, okay, so this was our vertical asymptote, and then we had 3x plus 3 as our oblique asymptote. So the graph in red is the actual graph. And then just to show you what those lines would look like. So you can kind of see that's your x-intercept on the negative side. That's your x-intercept on the positive side. So we have those positive and negative square root of 4 over 3. You can see that's your y-intercept. So we definitely have all of those points. But then what's happening on this left-hand side arm of the graph, as it goes up, obviously it's getting blocked by the vertical asymptote. So it's going to get closer and closer to the vertical asymptote. But remember, these will never touch, never cross. As you come down that, once it crosses the y-intercept, then you can see it starts getting blocked by the oblique asymptote, right? So again, it's going to run basically alongside the oblique asymptote, not touch, not cross. On the right-hand side of the arm, it's kind of coming from where the vertical asymptote was, crosses the x-axis. And then at this intersection where the two asymptotes kind of meet, it changes direction and starts following the oblique asymptote. So basically on both sides, it's going to be blocked by the vertical or the oblique asymptote. And again, you can kind of see how different this graph ends up looking like compared to the ones where you have both vertical and horizontal asymptotes, because obviously the oblique is gonna do its own thing. So just to kind of show you guys what an oblique asymptote graph may end up looking like. Questions on this example, you guys? So I'm actually going to save this, just so you guys can have a look at this. Where am I? This is actually similar to the example we did before, because this is not in lowest terms, so you will be able to reduce this down into lowest terms, so this graph will end up looking a little bit different. And again, I'll actually let you guys look at that example through the lecture notes or the video lecture. Let's talk about rational inequalities. So we have at this point talked about quadratic inequalities, how to solve them with graphing and test point method. We did the same thing with polynomial inequalities, how to solve them with graphing and test point method, and now we're getting into rational inequalities. So again, you can see rational inequality can be anything such as the example over here, x plus 3 over x minus 2 less than equal to 2. Basically, as long as you have a polynomial on the numerator, polynomial on the denominator. So we'll see how we can solve these using the graphical method and the test point method. So this one over here is talking about using a graph. And you can see this example 8 is kind of very similar to the one over here with the example 7, because this was also not in lowest terms. And number 8 is very similar to that. He is also not in lowest terms. So we do actually need to come up with a graph for number 8 before we can solve that inequality. So same starting point. What is our vertical asymptote for this guy?
This one is 4.
No.
Oh wait, vertical, yeah. Two. Oh yeah.
It will be
Plus
plus
minus
or minus 2. Yeah, very good. So that denominator, basically, again, you can write it as x squared minus 2 squared. So it factors into x plus 2, x minus 2, set it equal to 0, which will give you plus or minus 2. So just since we are talking about the graph, its domain, of course, then comes from negative infinity to negative 2, negative 2 to 2. Since you're leaving 2 numbers out, it's going to break it up into 3 intervals. Okay, so positive 2, negative 2. Now, can you tell me if this side will have a horizontal or an oblique asymptote?
Horizontal.
Horizontal, because the degree of your numerator is less than the degree of the denominator. You have a horizontal asymptote at the x-axis. Okay, so y equals 0, which is of course this line over here. So, like I said, this guy was not in lowest terms. You've got x minus 2 on the top. The denominator, like we just saw here, can be factored out into x plus 2, x minus 2. So of course, the x minus 2 will cancel each other out, leaving us with 1 on the top. It does not disappear. You will have 1 on the top and x plus 2 on the bottom, which that function, when you put it in lowest terms, it kind of looks like the only number you cannot use here is negative 2, right? But from the original, we know we cannot use both positive and negative 2. And what will this graph end up looking like? Again, if you guys were doing this by hand, we would do the x and y table, pick some numbers for x, throw them into the function, find a value for y. But again, we're just going to use technology to help us out. Where did you go? So we are trying to graph 1 divided by, what was it, x plus 2? So what are you noticing over here? How many vertical asymptotes did we say, or at least 2 numbers that we could not use?
You have two asymptotes and it's crossing the positive two.
So how can we modify that? Because we obviously don't have 2 vertical asymptotes here, right? So how would we need to make sure we know that we're still leaving the x equals plus 2 and minus 2 out? Oh, we saw that in that one example on my math lab. Jocelyn, do you have an idea? How would we leave x equals plus 2 and minus 2 out? Let's go back to our. So technically, there's 2 x values we cannot use, right? Positive 2 and negative 2. However, when we look at the graph, it kind of looks like we don't really have this. Very nice. That's exactly what you need to do to leave that positive 2 out, is create an open circle. And that's my problem with technology. Yes, it helps us, obviously it took us like 5 seconds to come up with the graph, but it doesn't get into all those nuances that you need to be aware of. So make sure you understand there's gotta be an open circle here at the positive 2. So when we actually do this, man, I don't know what happened to my bottom line over there. So when you draw this, oh, where was my graph? Okay. So it's coming down here, so it's blocked by the horizontal asymptote here, it gets turned around by the vertical asymptote here. And then this guy is coming here, you do actually have a y-intercept. And then we're gonna leave an open circle here at positive 2. And then you kind of go along with it. So again, like I said, you could have found your x-intercept, y-intercept, which looks like we actually wouldn't have an x-intercept once you look at the function in the lowest form. If you try to find the x-intercept, remember what I told you, just take the numerator and set it equal to 0, so you would actually end up getting 1 equals 0, which there's no x value. So you have no x-intercept, and that's pretty evident from our graph because our 2 arms are not crossing the x-axis anywhere. To find your y-intercept, we would of course set the x value equal to 0, so you would end up with basically 1/2, and you can see that we do actually have a y-intercept here, and you can see that over here as well. Right at 1/2 for the y value. So we do have an y-intercept, but there is no x-intercept, and again, you can kind of zoom out if you wanted, and you can see we're not crossing the x-axis anywhere. These arms are just getting close, but as you zoom in, you'll start noticing the gap in there. Okay, so the graph is literally just an important part actually, because we're trying to solve the inequality. The graph is just helping us with that, and for some reason he's not wanting to cooperate, but you guys have a general idea of what the graph looks like. So now our inequality was when is your function greater than 0, basically? So I'm just gonna write that out over here. X minus 2 over x squared minus 4 is greater than 0. So basically we are saying so you're basically saying when is y greater than 0? So which part of the graph, bless you, which satisfies our inequality? Where is y greater than 0?
The right side.
The right side. So look at the left-hand side of our graph here, and that's the graph in the red. You can see all of that graph, the left-hand arm is below the y-axis, right? Which means all my y values are going to be negative on this side. So for this whole section here, your y value is going to be negative. So that's not my inequality. Obviously, at this point over here, well, no, we were still at 1/2, right? So we're okay on that. Yeah, so this whole arm of your graph is going to be greater than 0. Now, how would you write that interval for the right-hand side, where the y is greater than 0? How would you write that interval on the right-hand side?
It would be, -2 with the parenthesis to +2 union, and then +2 with the parenthesis to the big.
Very good. So it's not negative infinity, right? Because you have that vertical asymptote, so we know we're just starting kind of adjacent to it, right? So yeah, very nice. You are beginning, this is your -2 here. And then we were also not using the +2. So this would be your solution set. Like Diego mentioned, -2 to +2. So that's going to be, between these two numbers here, that section, and then union, pick on the other side of 2, and then yes, you are headed to positive infinity on the other side. And again, remember, because the original function told us that we cannot use +2, that's the reason why you're putting the open circle in there. So when we reduced our function, the only number that we couldn't use was -2, and we see that because that's where our vertical asymptote is at -2, and that's actually coming from the reduced function. But we cannot ignore the fact what was my original function and where we started out with, and that one told me, yes, we did actually have two numbers we could not use. So technically, your vertical asymptote, because we are reducing the function down. Oh, let me just erase that part. So technically, your vertical asymptote is only at -2. Of course, we have our horizontal at the x-axis, and then from the domain is where we know we cannot be using 2. So think of it that way instead of 2 vertical asymptotes, because technically you don't really have 2 vertical asymptotes. And this is honestly the same exact thing that's happening on number 7. You just have 1s in there instead of a 2 and a 4, but it's the exact same.
So for the domain, since we're not using any of the negative values, would we still include that negative infinity coming -2?
Well, I mean, it's still part of the whole function, right? But this just did not satisfy our inequality, but it's still part of the original function. So yeah, in the domain, you would still keep that negative infinity to negative. Yeah, very good. Anybody else? Any other questions on this? So again, remember, this was just, you're given a graph. How do we interpret the graph to come up with our inequality solution? But again, graphs are not always going to be reliable. So that's where we always depend on something a bit more concrete, more algebra based, and that's where the test point method comes in. So basically, they're telling you, when you're solving the test point method is start by rewriting your inequality, if necessary, with 0 on one side. And then your ratio of the polynomials on the other side, make sure they're in lowest terms. So this would be the example kind of where you can see how that guy didn't have 0 on the other side, it said less than equal to 2, so that's where we would need to make sure we bring the 2 over to the left-hand side, get 0 on the right-hand side. And then, of course, you want to make sure your polynomial is in lowest terms. Find all the zeros of your polynomial functions in the numerator and denominator. So they're basically saying, set them equal to 0, see what your, basically your x and y intercepts come out to be. The rational function is undefined at the zeros of the denominator, so they will basically give us where our vertical asymptotes are going to be. So setting the numerator equal to 0 gives us our x-intercepts. Setting the denominator equal to 0 gives us our vertical asymptotes. Locate zeros from 2. So they're actually talking about this step here. Locate zeros from 2 on the number line and a test point in each interval, like we did with the other functions. And then, of course, we see where our interval is going to be positive, negative, greater than 0, less than 0. So let's take a look at this example over here. Actually, let's see what my math lab example looks like. Yeah, let's do this guy. Solve with the test point method. You have x plus 4 divided by x plus 6 greater than equal to 0. So no graph in this example. Start by, well, we've already got 0 on one side. That's already in lowest term. So we can start by taking the numerator, set it equal to 0. Denominator, set it equal to 0. This guy will give us -4. This guy will give us -6. Now remember, the denominator gives us the vertical asymptote. The numerator gives us the x-intercept. Each one of these creates an interval on your graph. So when you set up your number line, guess I'll do it here. This will be going towards positive infinity. This guy's going towards negative infinity. Let's see, -6, -4. Okay, so those are the 2 zeros from our rational function. So I need test points from each of the intervals. So what can be a test point here, here, and here? Let's start with the left one. What can be used for the test point there between negative infinity and -6? Sure. Okay, between -6, -4. Yeah. Very nice. And then -4 and positive infinity.
8.
Okay. All right, so we have our test points now. Obviously, you put it back into the original function for the y values, because remember, basically, these are all x values. And then we try and see, do we get positive or negative? Honestly, you could even get 0, but let's hope not. All right, so let's start with x equals -8. Putting it into the original function, we would have -8 plus 4. On the bottom, we would have -8 plus 6. What will that give us?
Over -2, which is +2.
Very good. Yeah, so you get -4, -2, which comes out to be +2. So your y values are actually going to be positive in this interval. Okay, next one was x equals -5. So let's see, that would be -5 plus 4, -5 plus 6. And what does that give us, guys?
Just negative one.
-1. So let's see, -1 from here, +1 from here, so you have -1, which means y values are negative in the center. And then the last one was x equals +8 in this case, so let's see what would that be. 8 plus 4. 8 plus 6.
We just did that 12 over 14 and going to 75.
I mean, yeah, it's a fraction, but we get basically 6/7, right? But the idea is we're actually more interested in the sign that you're coming up with, which that will be positive. Okay, so this is our inequality, greater than equal to 0. Where is your y value equal to 0 at? At the vertical asymptote or at the x-intercept? Or both? X-intercept, yes.
Why is it?
Say that again?
Wait, why is that the x? Oh, because it's -4, 0. This is the x. Okay.
Because you make your y value equal to 0,
Yeah,
right?
'cause
So
that's
it's fine.
the one on the bottom is.
And then, at the vertical asymptote, obviously, there's gonna be no graph going through that number, so you're not really gonna have a y value there. So there is actually no y value here. So since this is an inequality that says greater than equal to 0, we do need to know where our y value is equal to 0. Which would be right here, your y value is equal to 0. So looking at our little number line over there, where is your y value positive and equal to 0 at? What would that interval look like?
Negative.
So we're looking for y values. Basically, this is telling us y is greater than equal to 0. So where the y value is equal to 0 and where the y value is positive.
So just -4 to positive infinity.
Nope. First, let's look at where is your y value greater than 0 at what intervals? Dawson, any idea?
-6 to
Say that again, I didn't catch the first part.
So -6 to -infinity is all positive, and then -4 to infinity.
Yeah, exactly. This is the section where your y value is greater than 0. Y value is greater than 0, and then right at -4, y is equal to 0. So that becomes the interval from -infinity to -6. Obviously, we're not including -6. -6 to -4, y values are negative, so we can't really use that. So union, how do I write that last interval?
So bracket -4.
Yeah, because you are including -4, we must put a bracket at -4. And then we'll go all the way positive infinity. Okay, let's type this guy in. Okay, -infinity to -6. Parentheses. Where's my union? Okay, there we go, union. Bracket, where do we go? -4 to infinity. Okay, apparently it's not gonna let me. All right, questions on this one, guys? So really have to be careful about what that inequality symbol looks like, greater than, equal to, less than, equal to, or just simply greater than or less than. So you have to be very careful, because the inequality symbol guides what your solution set's going to look like. Okay, so that's just an application. Let's talk about this example over here, since you don't have a zero on the other side. What will this function end up looking like when we get zero on the right hand side?
Just minus the one, so.
Yeah, so subtract that one, bring it over to the left hand side. So you would have 1 over x minus 1, and then we'll be subtracting that 1, bringing it over so that we can have 0 on that one side. Now you would need to simplify this, put it in the rational function format before you can solve this. So how can I simplify this then? So you would need to do common denominators to try and combine them. Just trying to see if I have enough space here to work on this. Let's see. So basically, to find a common denominator, we would need to multiply this right hand side by our x minus 1 denominator here. So that would end up giving us, of course, this fraction is staying the same. We have that minus in the middle. And then you've got x minus 1 over x minus 1. So start by finding your common denominator first. The reason why I left the numerator in parentheses is because of this negative sign over here. You will need to distribute that negative sign inside, which will end up giving us 1 minus x, negative and negative is positive 1, and then you have your common denominator of x minus 1. So just clean up that numerator. And of course, all of this is greater than equal to 0. What does that numerator clean up into?
2 minus x.
Yeah, so 1 plus 1 will give you 2, and then you end up with 2 minus x. Okay. So 2 minus x, x minus 1 greater than equal to 0. So clean up your function before you start worrying about graphing it, test point method, whatever they ask you to do. So now we're ready to do the test point method. So this is where, again, take your numerator, set it equal to 0. Take your denominator, set it equal to 0. So what do you get for the 2 minus x equal to 0? Yeah, just add the x to both sides to keep it positive. Is this my vertical asymptote or x-intercept?
That is your x.
Very good. This is x-intercept. And that's the vertical asymptote. I knew I was gonna run out of space. Oh, well. Okay, so let's draw our number line, positive infinity, negative infinity, let's see. We have 1 and 2. So, let's pick our test points. So from negative infinity to 1, what can we use as a test point?
Or 0, sorry.
Okay, good. It's gotta be something smaller than 1, so yeah, 0 works. Between 1 and 2? Yeah, you are gonna have to go with decimal or a fraction because there is no whole number in there. So if you wanna put it in decimal form, you can do 1.5. And then between 2 and positive infinity. Yeah, 3 works. Okay, so same drill. We're basically trying to find where the y value is gonna be positive, negative, and 0 at. So y value is of course going to be 0, right where your x-intercept is. So remember at this point, your y value is 0. Now let's see for the other test points. What do we have? So this would be when x is equal to 0. Your y value will be, and remember you're using the 2 minus x divided by x minus 1 as your function now. So 2 minus x divided by x minus 1. And what does this end up giving us? Very good. You will get 2 divided by -1, which would be -2. This was for 0, so y is negative on that left-hand side. For x equals 1.5. Okay, so let's see, this guy would be 2 minus x, and then x minus 1. So what are we looking at? Three?
Actually.
1? Yeah.
0.5.
Maybe 1.
0.5, 1, okay, so of course, 2 subtracted 1.5 will be 0.5. 1.5 minus 1 would also be 0.5, so yeah, it's the same number divided into itself. You will end up getting 1, but more importantly, be a positive 1. So on this interval, y value is positive. And then the last one is x equals 3. So that would be 2 minus x. And then x minus 1. And what do we get for him? -1. Yeah, you will end up with -1 on the top, 2 on the bottom. So y value is negative on that side. Okay, so remember your inequality is greater than equal to 0, so we're basically saying where is the y value greater than equal to 0? So what interval are we looking at?
Between 1 and 2. Since our intercept is 2, we put a bracket.
Okay, so tell me what that notation looks like.
Parentheses 1. 2 bracket.
So you can see the only place where our y value is greater than 0 is in that center, right? So that's between 1 and 2. But then since your inequality had equal to also, we need to include where y is equal to 0, which of course happens right at 2, and that's why we are putting a bracket on the 2. And so you can see the tail ends are not being used, so we didn't have to worry about including negative or positive infinity because that's where the y values were negative, right? This application over here, so you don't actually have applications as part of your homework set, but this was just to kind of demonstrate how applications work with rational functions. So this one, as you can see, is actually a pretty simple example. This one is saying a truck rides for $100 a day. So that's your flat fee, right? And then it's 80 cents per mile. write a function that gives the average cost per mile for 1 day rental. What happens to the average cost per mile as the number of miles get very large? So is this even going to be actually a rational function in defining it? How would we come up with that cost function here? They're talking about write the function for the average cost per mile. So let's start by talking about the cost. What is it going to be? What is the cost function going to look like to rent this truck? How would you write it out? We actually did something similar to that first part in, I know, like 100 years ago, but that was chapter 1. How do you calculate the cost of renting the truck?
Would it be 100 plus 0.80x
And what does the X represent?
the miles driven?
Yeah, very good. So X will be the number of miles. So then you are looking at $100, which was your flat fee, plus the 80 cents per mile. So this actually gives you the cost function. Now they're actually asking you to write the average cost. So what would we need to do then? To convert this from the cost function to an average cost. Because they're telling you it's gotta be the average cost per mile for 1 day. That's the function you're trying to find. So there's one more thing we gotta do to modify this step.
Would you divide it by the number of miles?
Very nice, yes, because they're telling you what is the average cost per mile, which is divided by X, and that will give you your average cost. So they're saying now for the last sentence, what happens to the average cost per miles as the number of miles get very large? They're actually asking you how the horizontal asymptote looks, basically. Because when X gets really large, which means, I mean, obviously miles, you're not going to infinity, but that's the thought process, is when those miles get really large, what's happening to your overall average cost function? So the degree of the numerator is same as the degree of the denominator, right? They're both X to the first power. And what do we know from our horizontal asymptote discussion when the 2 degrees are the same? It's the leading coefficient. Yeah, very nice. So as X gets really large, and again, this is kind of hypothetical, your Y value would actually be heading towards coefficient on the top is 80 cents. This is, of course, 1. So what's gonna happen is the more you drive in 1 day, the cheaper renting that truck becomes, because you're kind of trying to compensate for that flat fee of $100. So the more you drive, it basically, you will be getting more value out of those $100, because if you just drove 20 miles, then this truck is gonna be expensive because you're paying 80 cents a mile plus that 100 miles. But if you drive, I guess, cross country, which I don't know, we can get to cross country, but you know, wherever that 1 day will take you, the more miles you have, the cheaper it's actually going to become to drive the truck. So that's kind of the idea of how do we use a rational function with horizontal asymptote, but put it into the context of an application. So that's kind of what this guy is displaying. So obviously there was not much of solving, but just talking about what happens to that overall cost as your number of miles get very large. So again, keep in mind, in practical sense, you're not really going to infinity. But we're just assuming, you know, what if you drive 500 miles a day or 600 miles a day, you know, whatever you're able to, you know, obviously without getting too dangerous. Alrighty, guys, so that's pretty much it for chapter 3. This is the last part, and then of course we get into chapter 4 after this. Chapter 4, I think it's 4 sections also. Yeah, so that may be our last like big chapter. Chapter 5 is only 2 sections, though we talk about 3 sections in chapter 5, because we'll review 5.1 just to make sure you guys are comfortable with those concepts. And then chapter 7 is also 3. So we're kind of halfway in terms of chapters, but we're more than halfway in terms of content. So you guys are taking chapter 3 exam on Thursday. And of course, that goes everything from what you did in section 3.1 to all the way 3.5. So remember, we introduced quadratics in 3.1, but then we kind of diverted into polynomials. We looked at different theorems of how to solve polynomials using the rational zero theorem, Descartes' rule of signs, theorem on bounds, and I know it kind of seems like, man, it's been a while since we talked about those. But that's obviously still part of this. How to do long division, there will be at least one question on long division in your test, and then everything else you can use synthetic division, so you will have that, and then of course this last section where we got into rational functions, so basically quadratics, polynomials, rational, so this kind of covers all 3 of those types of functions. As always, you guys are allowed a cheat sheet. I would probably say either do 2 of those 3x5s so that you have enough, because you do kind of jump around on topics, so if you need 2 of the 3x5 cards, that's okay. To get everything that you need. Same policies, no cell phones or tablets for calculators. So bring a traditional calculator, or we have the ones in that room that I can let you guys have for the exam. I'll provide you with the scratch paper, and then of course you guys can use your own devices for the exam itself. As always, just make sure I can see your screen and you guys are good to go. So that's from my end. Anything that you guys have questions about in terms of the exam?
There
Can we
was a-
do 3.1, question 5 on the homework?
3.1, question 5, sure. Go ahead.
Oh, I was gonna ask him about another question. on him.
Okay.
The application problem, I think at the end of 3.1, where they were talking about the perimeter. And it was the one with the barn that's a sign.
Oh, yes, I do vaguely remember that problem. What happened to my screen? Yeah, I knew I had done something funny. Okay, you said 3.1, number 5. What section was yours from?
Like 3.12.
3.1 as well, okay. So what's your question on this one?
Huh?
What's your question?
Can we just do it again?
Do it again. Okay, so you're converting this from the standard notation to the transformation, where you factor it out. Can you guys tell me how we walk through this example? So remember, this is where you're kind of using completing the square, but you're only using completing the square on one side because there's nothing you can do on the left-hand side. It stays as y equals. Additionally, you are actually only grouping the first 2 terms. And you're leaving that constant term kind of on its own for now. We don't mess around with it. So we would basically start by factoring out that -3 from the first 2 terms. Very good, that leaves you with x squared. Now, since this guy is negative, your sign will change on the inside, or the other thing you can do is, since 3 does not go evenly into 2, you can leave that as plus 2x, but since we're factoring that -3 out, you would need to divide -3. So that itself also takes care of the sign, because then positive times negative, we know will end up becoming negative anyways. So basically you're factoring out the -3, so you're left behind with x squared, and then just take that middle term and divide it by that number. Like I said, we're kind of leaving the constant term outside to do its own thing for now. Just to clean this guy up, -3 on the outside, x squared positive and negative becomes negative. And this will now become 2/3 x. For completing the square, what do we need to do?
You want to do.
What's our B value?
-2/3.
Very nice. Yes, it's going to be the coefficient of the x term, and you don't have to worry about the sign because square will always make anything into a positive, so we don't really mess around with that. So just take the 2/3. Now remember, guys, when you're working with fractions, it's the same thing as dividing by 2 would be the same thing as multiplying by 1/2. So that's probably the route we will go here. So B is 2/3. You're multiplying it by 1/2. And then we'll square the result. Now, in this example, you can actually reduce this, right? Because we have a 2 on the top and a 2 on the bottom, so you can actually cancel those out. When nothing cancels out, you just multiply across, but in this case, we are able to simplify that. So we have 1 on the numerator, 3 on the denominator, and then you square it. And go ahead and reduce that because it will make your life a lot easier. So don't leave it as 2/6, reduce it. What's the 1/3 square? 1/9. So this is the number that's going to be added and subtracted inside the parentheses to give us our completing the square. So -3 on the outside will stay as is. Inside the parentheses, x squared minus 2/3 x. Now remember, guys, we're not changing the value of our function equation here. So since we're going to be adding 1/9, we also subtract 1/9 because that's at maintaining the balance. Now, when we had talked about completing the square back with circles, we were adding that 1/9 to both sides of our equation. But since we cannot add anything to the left-hand side, you're adding and subtracting at the same time. Now, keep in mind, these are the only 3 terms we need for completing the square. So you're going to take that -1/9, multiply it with the -3, and then bring it outside and pair it with that -6. So take the -1/9, multiply with -3. What will that give us? So these are the only 3 terms we need inside the parentheses. Did you say 1/3? Positive, negative?
Negative. Very positive.
Positive. Because you're doing negative times negative, right? So they will become positive. I'm just bringing my -6 down. So that's going to be, and again, if you guys need to do this on the side to make sure, let's see, where was I? -3 multiplied by -1/9. 2 negatives become positive, you get 3/9, which reduces down to 1/3. So that's being added at the end. Okay, so that's basically the product of these 2 numbers, which is coming down here. So we'll add the -6 and the 1/3, but we need to factor the parentheses part. And if you guys remember when we had done this the first time, I had told you that that actually comes right before you did the squaring over here. So you've got 1/3 right before we squared it, and that's going to help you factor this guy out. So when you are factoring this, I guess we're gonna have to go here. 1/3, sorry, -3 on the outside. We're trying to factor this guy. So since you have a negative in the middle term and positive on the constant term, this is going to stay as minus. And then basically, if you think about it, 2 numbers that multiply to give us 1/9, so 1/3 times 1/3 will give us 1/9. And then 2 numbers that add up to give us -2/3, and of course, that would be -1/3 added with -1/3. So this guy will become x minus 1/3, and then the whole thing squared. And then what's -6 added with 1/3? So you can use your calculator. Or find a common denominator and add the two numbers together, but just make sure you leave it in a fraction form. So that's kind of what it takes, is using that, completing the square. Let's see, -3 x minus 1/3 square minus 17 divided by 3. Then they're gonna ask you to graph it. Before we get into the graphing part, Nate, questions? Helps you out?
Yeah.
Yeah. Anybody else questions on this? Jocelyn, did you have any questions on this? No? Now, remember, guys, when you are, okay. Graphing this, if I remember correctly, I think it has you do the transformation type of graphing in this one. So of course, this is a parabola. Let's see what happens. Yeah. So can you tell me what numbers we're going to be putting in for our graph over here based on what we just did with the transformation? Do we have a stretching or a shrinking factor in here? Yeah, what is it going to be? Yeah, so that's that a value right in front of your function. Oh. Well, looks like we're actually going to have to use reflections. You're typing in 3 in there. Vertical translation. That's right. I remember because that happened last time, didn't it? So what's the order for multiple transformations? Good. All right, so let's start with horizontal then. What's our horizontal translation here? So it will actually stay as positive 1/3 since you're moving to the right. Then we're doing the stretching, shrinking. Does the reflection happen in the x-axis or the y-axis? X-axis. And then our vertical. Oh, I forgot my 3. So it should be moving downwards. Save. Check. What number was your problem?
I think it was either maybe 21 and 20.
With the barn, you said, right? Barn. Okay. So this was coming from using that idea of maximizing, minimizing your area. So this is talking about a farmer decides to enclose a rectangular garden using 60 feet of fencing. What dimensions will maximize the area if the barn is used on one side of the rectangle? So technically that 60 feet of fencing is only going on 3 sides. Because you're just using the barn as the 4th side. And it honestly doesn't matter if you have 2 widths, 1 length or 1 length, you know, whatever I said, the opposite of that. So the idea is you're only using 60 feet of fencing for 3 sides instead of 4 sides. And I think the example we had done in class might have been 4 sides. So this can be width, length. So 2 times the width plus the length will equal 60, and that basically is your perimeter, right? Now the question is about maximizing the area. So remember, area is length times width, but we want to convert it into one single variable instead of multiple. So if you wanted to get length by itself, we can go ahead and subtract the 2W on both sides. So using that perimeter, you're basically just rewriting either length in terms of width or width in terms of length. It doesn't matter which. It was just easier to get length by itself. Once you have this little conversion done, then we get into the area formula. So our length, you're now going to replace the L with 60 minus 2W. So this is the length, and then you're still multiplying it with the width. Okay? And then of course we end up distributing that by. So let's see, 60 times W minus 2 times W squared. And you can see this is where our quadratic function shows up, is once we take the perimeter and put it into the area formula. So when you're maximizing the area, which characteristic do we need? The vertex. The vertex, very nice. Do we know what that formula for finding the x value in the vertex is? Very nice, negative b over 2a. What's the b value in this function, guys? Very nice, so that becomes negative 60 on the top. A value? Negative 2. So that's the b, that's the a. And what does this clean up into? So negative 60, negative 4 equals positive 15. So remember, that's the width. They don't really want to know what the area is going to be. If you wanted to know the area, we would take that 15 and put it back into this function. They're just interested in the dimensions, right? So the next thing you want to find out is the length by using this guy over here. What does this come out to be?
And will there be application problems in the exam?
Yes, yes. Either this guy or the other one of them will definitely show up. So let's see, the larger dimension. And this is gonna be feet. Larger dimension was 30, smaller dimension was 15. Jen, does that help you out? Yeah. Anybody else have questions on this example? Jocelyn, are you okay with that? Yeah. Anybody else have question on homework? Okay, I'll be available through email, guys, if you do have questions on homework, all right? I have office hours today and tomorrow, so let me know if anything happens. So good luck, everybody. I'll see you for the exam on Thursday. Take care. Yes.